talk a little bit about the history of chemistry, of atoms, molecules, and compounds. And this is going to be a review of something we talked about in chapter 1. In back in the time of ancient Greece and ancient Egypt and all these wonderful ancient uh, cultures, they actually started thinking about what the world is made up of. So Democritus is well known for his theory that these things called atoms, which are Greek for indivisible. He just he just had no proof. He just thought of it that if you looked deep enough, you'll be able to see that any material, no matter what it is made up of these indivisible things. You can't just divide them further. Okay, that theory was largely abandoned for thousands of years until the British scientist John Dalton came up with his own theory, which was based on things that have been observed at the time, but they were unified afterwards. So he said that some materials are elements and some materials are compounds, very similar to what we said in chapter 1. These are all known as pure substances. Elements are made up of atoms, as we said, so iron and sodium and fluorine and helium. These are all atoms. And if you look at all of helium in the universe, all helium have the same properties. Helium has different properties than, say, iron or copper. Atoms of one element cannot become atoms of other elements. You can't just randomly go from, say, silver to gold. So he just disproved alchemy. He said that compounds are two or more atoms that they combine, just as we mentioned before. It's basically a molecule. The smallest unit of water, H2O, is a molecule of water, H2O molecule. And if you try to break that even further, you have to do a chemical change to it, and then you will form H's and O's, and those are not water. So he said that things are in definite proportions, just as we mentioned in chapter 1. This is just his ideas. And he also brought up the idea of the law of conservation of mass. That you cannot destroy mass and you cannot create mass. Mass is a conserved property of the universe. All right. So that was it in the 17th century. As we advanced and chemistry became its own field, and physics, it came out of really broke away from physics. Subatomic particles were actually discovered. So the atom is not as indivisible as we thought it was. Okay. These cathode rays had been discovered, and they didn't know what they were. But a scientist by the name of J.J. Thomson noted that when electric field is applied to cathode rays deflected away from the field. Okay, what does this mean? Here, opposites attract, but likes hate one another. They repel. So when a negative hang out, they repel. They don't want to be together. Opposites want to hold hands. They stick together like a magnetic thing. Okay. Don't eat that. That looks disgusting. So cathode ray deflected from the field, meaning that cathode ray is a bunch of negative stuff. So he then assumed, well, they knew that electric field is negative. It just is a negative field. And so he said cathode rays are made up of these negative particles. Let's call them electrons. Okay. All right. So he noticed that atoms also interact with cathode rays, and so that there's no way that atoms don't have these electrons in them. He's like, atoms probably have some electrons. That's kind of cool. And so he noted that atoms themselves are neutral, but inside there are electrons, and something that makes them neutral for every negative, I have a positive, so it's zero. And he called those protons. And he came up with a plum pudding model for the atom. And this is what a plum pudding thing looks like. I've never had plum pudding, but they keep using that as the name of the model. That's what he came up with. It's a British thing. And he said it's basically a sea of electrons. It's a sea of protons. The red is a sea. It's like an ocean. And in it, a bunch of islands that are each electrons. That's what he thought. It's wrong, but that's what he thought. And for a while, that's what people thought the atom looked like. But that's not true. So then Ernest Rutherford said, okay, all right, if you're right, then if I shoot a bunch of positive stuff at gold, right, and there's a bunch of negatives in it, then it will get attracted and all of it will go through. That's what he thought. Everything's going to go through. Okay, so if your model is right and I shoot positive stuff into this thing, negatives like positive, it's going to shoot right in. It's going to go right inside, no problem. This is what he actually noticed. He saw a bunch of these things come out, which he said, okay, that kind of makes sense, because if I'm shooting positive at this stuff, the positives that are here are going to shoot back fine, no problem. He noticed that a lot of them actually returned back to the source. He said, what's going on with that? Why am I getting stuff going 180 degrees away from where it started, right? That made no sense to him. Then he said, probably it looks like this. I'm shooting positives at it. J.J. Thomson's model is incorrect. All the positive is actually in the center. That's why I'm getting it coming back at me. And there's no positive here or here or here or here. It's all negatives, and that's why it's deflecting away. It's being attracted and it's going different ways. And I'm getting a lot coming back at me. Okay, so he changed the model. This is called the gold foil experiment. He changed the model of the atom to look like this, with a big positive in the center. And he said that the center of it is called the nucleus, where the protons hang out. Okay, and the electrons go around the nucleus. Okay, atom, they said, is mostly empty space, which is why most of those rays went right on through, because most of it is empty. Right? Chadwick in 1931, which sounds like a long time ago, but it's not. I mean, the grand scheme of things, Democritus is 3,000, 4,000 years ago. The neutrons were discovered, I don't know, 90 years ago. It's pretty recent. Said, okay, inside the nucleus are also these neutrons that have no charge.